Hey everyone, so my name is Ron Ribbensaft. I'm going to speak today about something that everybody is experiencing on their day-to-day, errors. Who had an error this day or this week? Yeah, great, everybody. So I'm going to talk about errors, retries, and other things that happens in stateless environments, or in other words, serverless. Just a bit about myself. I'm the CTO at Epsagon. We got our booth there, so if you're interested in learning more, just come by. I'm an AWS Serverless hero, which means that I'm eligible to tell lies about serverless and Lambda and other things. And here I'm trying to look for whales in a Y, but I couldn't find any. So if you can find something, let me know. I'm also available on Twitter. Before we even start, I want to speak about what is serverless, the history of serverless, where we got, and how do we got to this point. But no, actually, I'm not going to speak about it because I think we already spoken about it a lot. Instead, I'm going to dive into some more technical stuff. Errors, retries, distributed tracing, things that happens in every day-to-day application, and we need to make sure that we can overcome them in the right way. So let's take an example application. I really like Goico example that you have some built-in integrations, but in this case, I'm streaming events for my customers, for example, for tracking or for any other purposes. I'm going to set up an API gateway so I can get them through an HTTP endpoint for my customers. I'm going to stream it directly to a Kinesis for main reason that I want to respond fast to my customers. It means that they're waiting. I don't want them to wait a lot. I want them to get a response as fast as possible. And also, I want to batch things all together. I don't want to process each event individually. And then I'm going to put a Lambda that will do some enrichment, transformation, processing of the data, and then it's going to store it to a DynamoDB. Usually would grade this application like 9 or 10 out of 10 in the serverless score, right? Because everything is serverless and errors cannot happen anywhere in the code. But that's not actually true. Errors can happen in all of these services. Let's try to focus on just some of them, okay? Maybe the Kinesis. So unfortunately, Kinesis handles shards, and you need to configure your own shards. Each shard has some limitations in terms of the input and output and how many Lambda functions it can trigger concurrently. To solve it, for example, we can either manually adjust it. We only got 10 retries or 10 times per day to do that, so try not to be so flexible. Also, we can improve the distribution. For those of you who aren't familiar, when you put a record to a Kinesis, you choose a partition key. This partition key will derive into the right shard that you're using. So if you're not doing it right, it happens to be that all your messages will get into the same shard, which is a no-no case, or automatic shard scaling. I hope that AWS will do that built-in someday automatically. Secondly comes the Lambda, where this is our code. It can have some exceptions. It can have timeout or out of memories, which all can happen in serverless environments. Now here I don't have a great tip, just write a better code or measure your functions or do other things. But I'll talk about some best practices in how to overcome such issues. And also the DynamoDB. Up to until recently, we needed to configure the write capacity units and the read capacity units, like how much concurrent writes or reads we can do to that DynamoDB. So if we had too much scale, we were just getting some exceptions from the DynamoDB. Today we can use auto-scaling with a small mark. Make sure that it's okay with your cost, because that means that the cost is much more flexible. And if you're having more scale, you're going to pay more unexpectedly. So once we understand these kind of problems, there are lots of other services to consider. This is just some of my favorite ones, like IOPS in RDS, even the Aurora one, or Firewall's batching size, or Athena concurrent queries. Almost every service got some limitations that you need to make sure that you're taking care of. Let's talk now about how to overcome such errors. So what are the best practices when we're having errors in any scenario? So first thing to understand is middlewares. Middlewares acts just like a middleman, or like when you're peeling an onion layer after layer. Where we can use it, for example, in a Lambda function that every time before we're getting a request or after we sending the response, we will add some logic that will be applied to all of our functions, and we're going to write it once and for all. For example, measure the duration from start to end because we want to make sure the performance is working well, or to print some verbose data about the event if we need to troubleshoot it, so we'll have it afterwards. Use correlation ID, capture errors, which is also a great example, and it's pretty easy to do that. You just need to make sure what's your great recipe to overcome, to do it right. I'm going to recommend MIDI. MIDI.js is one of the most popular middleware engines for Node. And you can see how simple is that. So you can, let's say our process payment, this is our Lambda function handler. In order to add some more middlewares, I'm just going to use event logger that behind the scenes logs the event data, timer that will print the duration afterwards, and HTTP error handler that will take my exceptions and propagate them in a right way outwards to the outside world. So these were middlewares. We also got dead letter queues. When we're having a problem, remember the scenario that we had. If my function is going to fail, there is a built-in retry mechanism, and we're going to talk a lot about retries, but let's for a moment say that there is going to be a retry. My Lambda function will fail. Kinesis will try to put again the message sometime later on. And it will retry that over and over again, I think up to a day or 7 days, really defined by what you measure. It's going to create some bottleneck in your application, because if many people are going to stream some bad messages, not on purpose, just because the code don't handle them, it's going to create a load or a bottleneck in your application that you just can't escape from it. You're going to have tons of messages in your Kinesis that you just can't unleash somewhere out. And specifically for that case, we got dead letter queues, or in short, DLQs. DLQs helps us to stream out bad events or events that we can't handle towards some other queue that we will be able to process them in a different way. For example, and by the way, it's built in for SNS, SQS, and Lambda functions. Let's say I'm having a bad time on my Lambda function, and I just can't parse this kind of message. I'm going to stream it to some DLQ, specifically Q, that I'm going to store it into S3, for example, the old message outside, so I'll be able to manually review that afterwards, so I'll understand what went wrong, or I'll retry that at some other time when I'm fixing my problems. So these were DLQs. And another thing to note, once we're having errors, I would say for me the most important metric to look at is Iterator Age. And in other words, it says, what is the oldest record that I'm currently processing? And it means that when it grows, when Iterator Age metric growing up, it means that it takes me more time to process the input than generate output. It means that I'm creating a delay. Usually such things happen when my application is scaling up, or I'm getting more requests, or the services that I'm using can't handle this amount of traffic. Usually it comes with when we're having services that are not fully serverless, like RDS, for example, and we're having too much concurrent functions and it's taking slow, and we're having more errors. In this example, by the way, this is real from Epsagon. We had such issue. We had a lot of issues almost for every software, but it gotten up to the point of 1.4 million milliseconds, which in other words translate into 24 minutes delay, which is a lot. It's not good. It means that people can't see their updated information. Another thing, and I think almost everybody in the room talked about it, is to make sure what's our current configuration for memory, because this is the most easiest way to improve the performance of our Lambda function. Alex talked about it. Memory impacts CPU and network. It means that you're having more memory, you're having more shares for that CPU and network. And just as a quick tip, or even before the tip, look at another benchmark that we've made, especially like one for Python doing some heavy calculation. When we're running on 128 megabytes, almost 400 milliseconds on average. But when we're multiplying by 4, we're getting 4 times faster function. It means that we're paying the same amount of price, but our function runs 4 times faster. It creates less bottlenecks, and it means that all of our flow is running smoother. Now, just as a quick tip, I know that everybody in the room says, I know how much my code consumes in terms of memory. I always benchmark it, which actually nobody does, but you're probably saying that you're consuming less than 128 megabytes because who who consume more than that. But it's not the right way to pick the lowest amount of number. Instead of it, try to pick even a higher number. As a quick suggestion, if you're using HTTPS calls, which consumes a lot of TCP handshakes and SSL certifications, try to set the bar into at least 512 megabytes. It improves dramatically most of the functions today. And another thing is just make sure to benchmark your function. Especially the high concurrent ones. I'm not talking about the ones that are getting an invocation once per day. I'm talking about the ones that are having millions or tens of millions of calls every day or every hour. Measure them, because one slight move in this slider can cause a big impact in cost, in performance, and all of this. Does someone knows about it? Yeah, that's a joke. Thank you. We're having problems. Every day we're having problems. We used to have this problem a lot back in the days. Usually what we did when we had this kind of problem, it's to retry. Just, okay, there is a problem, let's reset, let's retry the message, let's do that thing again. So let's talk about retries. And within serverless, we got something out of the box that it's a bit different than what we were used to do. With serverless or with Lambda functions, we got plenty of integrations to work with. You know, tens of services that are out there just waiting to trigger your Lambda function. And we can distinguish them into two main categories, synchronous and asynchronous. Synchronous ones, for example, like API gateway, derive from a set that the retry responsibility is on the caller. So for example, if I'm calling some service on HTTP and it fails, and I'm getting like 500 or 400, it's my responsibility to call it again sometime later to retry and get a response this time. Async triggers, for example, such as SNS, the responsibility turns into AWS, which means that they are going to retry your message over and over again. Though this makes sense because when I'm putting a message into SNS, I can't really know for sure what somebody else is going to do. I'm not even sure who is the subscriber of this topic, so I can't really know that whether it succeeded or not. So for these specific examples, AWS is responsible for doing retries. And now we can even configure the way that they retry to run again and again. For example, with Lambda function, now in the console, you can choose how many times you want to retry when you're calling function asynchronously, and how long will be the age of the event. I mean, how further are we going to try to invoke that message? For SNS, it's even a bit more complex. You can define how many retries, what is the interval between each and every retry, what is the maximum one, what is the backoff function. We're going to talk about exponential backoff soon, but what is the backoff function? Lots of configurations to do. And you know, I know it makes you maybe a little bit dizzy, but when you're handling lots of events, every needle in this configuration can impact drastically the performance of your application, especially when you're having problems. As we know, everybody have problems. Also, you need to be aware when you're having a retry. This is pretty straightforward to say that, but very hard to implement. How do you know when you're having a failed function that is being triggered by an SNS that it was failing? So for example, with Epsagon, we built in a way to understand it, and you know that you had an error number 1 which failed, 2, and 3. So you're at least being aware of this kind of retry attempts being transmitted to your applications. Retry attempt can be hazardous for your application. Let's take another example over here. We're having an SNS, then it triggers a Lambda function, then we charge the user on Stripe. Let's say it's something that we get notification about user purchases, and then it sends a confirmation email back to the user telling him, hey, you got your new product, thank you very much for buying an item. Now, what happened in this scenario if we're having a failed SES event? For example, we tried to send an email, but something crashed dramatically in the code. So it means we're going to have another retry after we already charged the user. We're going to have another retry, which will trigger the Lambda function, and then we will charge the user, and then we're going to send another email. But that's probably going to fail again because nothing changed in the last minute so far. And then it's going to happen again. By default, it's going to happen another 2 times. So it means 3 times that we're charging the user. I don't want to be that user that is being charged 3 times, and I need now to apply a claim to get my money back. It's a sad customer. You don't want to reach that point. So idempotency is the term that says we need to identify when we're having a retry and act accordingly. Identify is pretty simple. Accordingly, it means that if we had failed in the stage of sending an email, we're not going to charge the user again. How do we do it? Pretty simple. We either make our code non-crashable, which can't be actually done except you put all of your code in a try except block, which in most cases it's not the best case scenario, but sometimes you can't avoid it. The other one is to store session data in a DynamoDB, for example, and let me show you how that can be done very easily. So I'm having a DynamoDB. It got an hash key of event ID and a state. Once I set up this DynamoDB, every time that I'm getting an invocation, I'm going to need to create a unique identifier based on this event. This identifier can be my own generated ID. For example, if I'm having a purchase ID that I'm handling, this can qualify as a good ID to work with, because that's unique. If it's going to retry, it will be the same ID. Otherwise, I can use some built-in AWS services IDs. For example, SNS got a message ID. So if I'm getting a retry, it will stay the same message ID. Once I know that, I'm going to start my function. I'm going to call the DynamoDB and tell him, hey, do you have any state for this specific ID? If it has, I'm going to get a new state. If not, it means that I'm a new run. And if it gets a state, I need to go to the right state instead of trying from fresh. Also, I need to make sure that after every operation that I'm making, I'm going to set the new state, because once I'm charging, I need to update the DynamoDB that I charged the user. And in this specific example, we're going back to middlewares. This can be a great middleware that enriches one of our events with saying event.state. Now I know exactly where I am in the code. Another thing to notice when we're doing this kind of retries, or when we're having dependencies between services, even if they're decoupled one another, but they still rely on one another communication. So if we're having an issue on service B, something that creates a longer response time or more exceptions or something, it can really cause a delay on service A, because service B responds slowly. Service A waits for such response and then creates a bottleneck. And think of it, in other words, if service A is being bombarded by messages and now it's taking slower and slower to get replies from service B, it means that practically I'm denied of service. I can't get any more information. Users will get issues just because service A can't talk with service B. For that use case, we got a circuit breaker pattern. This pattern allows us to set some tripping mechanism, just like electrical design. Tripping means that I'm going to lose the connectivity between the two services, so it's going to trip out if we got some consecutive amount of errors, and it's going to time out for a certain period of time. So it means that I can say that if I'm having more than 5 errors in a minute, just trip out for maybe 10 minutes, or let the service rest and do some processing until it gets back. Again, the configuration here, it's really dependent on what your actual application is and how do you want to remediate such issues. Again, another example, great example on Python from GitHub for making a circuit breaker for Lambda functions, already set for you to use. Last thing that we're going to talk about retries is backoff functions. The most common one, or the most popular one, is linear backoff, as you can see on the blue line. It means that every second or every, constant amount of time, I'm going to retry. This is not so good because in most of the cases, if I couldn't make it in the first second, I'm probably not going to make it on the second and third and fourth one. So why try? I'm going to consume a lot of resources, and all will be resulted in the same problem. So instead of it, let's figure out the best strategy. And probably the best popular strategy, and again, it really depends what kind of exponential function do you define, but is to use exponential backoff. Gradually try to take longer and longer times and when we're trying to retry. So for example, do it after a second, then do it after 10 seconds, and then do it after a minute, and more, because we don't want to choke the services with not doing the right calls every time and again. Last topic that I'm going to talk about is distributed tracing. So far, we talked about a lot of scenarios, but being aware of such scenarios usually happen on one single case, when the application breaks and customers are calling and saying something is not working properly. But you don't want to reach that point when customers are waiting for you to fix problems. You want to be aware of them before that. Distributed tracing really allows us to solve complex problems, like how do I troubleshoot such complex scenarios? How do I understand that I'm having retry attempts? How do I know that Stripe call made it, but the SES send email couldn't make it? How do I monitor the end-to-end? How do I know exactly how long each part takes? How do I know if it creates a bottleneck or not? I'm pretty sure that all of these questions might sound easy to understand, but really hard to implement and get to the point. Especially for that, distributed tracing comes to help. Distributed tracing tells us a story of how a request is moving from one service to another in our system. So as you can see on the example in here, we got a request coming up from the client, moving to the load balancer, then the authentication service, the billing service, some other resources. I can easily understand with that kind of visualization where my request is moving from one service to another. I can understand how long it takes from one service to another and exactly what is the communication between one service to another. For this specific kind of problems, we got few open source tools. So 2 frameworks that defines the way to capture traces, open tracing and open telemetry, and one that helps us to ingest information and visualize it, which is called Jaeger tracing. Let me show you how to capture such a trace or how to do distributed tracing. So first we need to instrument every call. Let's say my HTTP calls that I'm submitting, so Axios, Fetch, GOT, Request, Net HTTP. In any kind of library, we're having this kind of HTTP calls, and we need to instrument them. Instrument means that every time that I'm making a call, I need to capture the information about the request and the response. What can I do with capturing the request and the response? Know, for example, which URL am I calling to? Know what was the latency between request and response? What was the status code in the response? So much information that can help me understand it. Then once I capture this information, I need to create a span. Span in distributed tracing tells me like this has been an operation with a start and an end time. After that, I'm going to attach some context because I need some context to that span. For example, what was the parameters in the URL, or what was in the headers of the URL of this HTTP call. Many things that allows me to get some more context about it. And most importantly, I need to inject and extract IDs. Because if I'm calling that service, I need to tell him, if somebody out there listening to my message, this is my ID 123. So if that other part somewhere in the world is listening and it's my service, is going to know that we're continuing request ID 123, and I'm going to transmit it over and over. So it means that I need to inject it into the request, for example, in the headers, and then to extract it on the receiver side. And ultimately, we need to ingest and index all this information, do something meaningful, alerts, and so on. It takes quite a lot of time. Just as a quick example, this is how do we do specifically in Python, capturing for HTTP, just the before request. So we need to start a span, we need to understand which is the active tracer, add some context, do a lot of information. It's okay that you can't read it. By the way, it's on opentracing.io. It's a lot of efforts just to make tracing run. And you don't want to do that. We're here to do serverless. We're here to focus on our business value, do what we need to do to make our companies better. That's exactly why we built Epsagon. This is a kind of a managed solution that is doing automated and agentless distributed tracing that is good both for monitoring and for troubleshooting. So to know when something is working or not working at the performance that we need, and also troubleshoot it when something bad happens and we need to make our hands dirty. And it's built specifically for serverless. So all these kind of scenarios that we just talked about are already supported. As we already saw before, this is just a quick screenshot from the product on an AWS environment using some third-party APIs. Just as a quick summary, so errors happen. We already know it. I think in the last 20 or so minutes, we talked about a lot of scenarios for errors. Retries is a good mechanism to overcome errors, but we need to know how to configure them and how to do them right, because otherwise it's not helping us. And observability, this kind of, especially distributed tracing within observability, is a crucial thing if you're moving to serverless and you're moving to production and you want to understand exactly what's going on in your application. Thank you very much.